You know the feeling? You're in your room, trying to concentrate, and you can hear it. That muffled thump, thump, thump of music from next door. And you look at the wall and you think, that thing is solid, so how in the world is sound getting through?
Well, let's get right into it, because the answer is this really cool journey into the physics of vibration. We're going to break down exactly how that seemingly solid barrier becomes, well, a bridge for sound.
All right, so to figure out how sound gets through a wall, we first have to ask a more basic question. What even is sound? It's probably not what you think it is.
See, here's the key thing. Sound isn't a thing at all. It's energy. It's a vibration, a wave, that has to travel through something, kind of like ripples in a pond. A speaker pushes on the air, creating a pressure wave that travels all the way to your ear.
And this is where it gets really counterintuitive. We think of air as the main way sound gets around, right? But check this out. Because the molecules in a solid are packed together so tightly, they actually form a superhighway for those vibrations. They're way better at passing them along.
So, knowing that solids are great at carrying sound, let's look at the main event, the wall itself. How does this big, solid structure actually move sound from one room right into the next one?
This is the perfect analogy. When sound waves hit one side of the wall, they don't just stop cold. Nope. They physically push on the wall, causing that whole surface to vibrate, just like a drumhead. It might be microscopic, but it's happening. And that vibration travels through the wall and shakes the air on your side, and boom, you hear the sound.
So when sound hits a wall, that energy has to go somewhere, right? It splits three ways. Some of it bounces back, that's reflection. Some of it gets turned into a tiny bit of heat inside the wall material, that's absorption. And the rest, well, that's the stuff that makes it through to the other side, transmission. The entire game of soundproofing is just to make that transmitted slice of the pie as tiny as possible.
So, how do we know if a wall is actually any good at its job? How do we measure it? Well, you bet engineers have a rating system for that, a way to score its performance.
And here's the magic number, the Sound Transmission Class, or STC for short. It's just a single number that tells you how much a wall can muffle sound. And the rule is super simple. The bigger the number, the more peace and quiet you're going to get.
But what do these numbers actually feel like? Well, a typical wall in a house might be around STC 35. That means you'll probably understand what someone is saying loudly in the next room. But get up to STC 60, like what you'd find in a recording studio, and you're talking about near total silence. Big difference.
And if you need any more proof about that sound a superhighway idea, just look at the speeds. Through the air, sound travels at about 343 meters per second. That's fast, but through steel, it's rocketing along at over 5,000 meters per second. This is literally why you can hear an approaching train by putting your ear to the track way before you can hear it through the air.
Okay, so obviously not all walls are created equal, and not all sounds are the same either. So let's look at why some walls are just, well, terrible at blocking noise. First off, we've got to know there are two main types of sound. There's airborne sound, like voices and music, that travels through the air and then hits the wall. But then there's structure-borne sound. That's stuff like footsteps from upstairs or hammering. That vibration travels directly through the building's frame, and let me tell you, that is a much, much tougher problem to solve. So a wall's performance really boils down to a few key things. How heavy and dense is it? How thick is it? Is there an air gap or insulation inside? And, this one's huge, are there any leaks? Because sound is just like water. It will always find the easiest path. Even a tiny gap under a door can let in a shocking amount of noise.
So, we get the problem. We know why our walls are failing us. How do architects and engineers actually fight back? How do they design spaces to be quiet?
Turns out they have a 5-part playbook. First, add mass. Think heavier materials. They're just harder to get vibrating. Second, and this is a big one, you decouple the structures. That means creating a physical break so vibrations can't cross over. Imagine 2 wall frames that don't touch. Then you absorb energy with insulation, you dampen vibrations with special materials, and finally, you got to seal every single leak.
In fact, there's a pretty reliable rule of thumb for this, called the mass law. It basically says that if you double the mass, the weight of a wall, you can cut the sound that gets through by about 6 decibels. And to our ears, that's a really noticeable difference.
Okay, let's wrap this up by looking at one last sound mystery that I'm sure you've noticed, and then we'll peek at where all this tech is headed.
You've definitely experienced this. You can't make out the song, but you can feel that deep thump, thump, thump of the bass line coming through the wall. Why is that?
Why does the bass get through when the rest of the music doesn't?
Well, it all comes down to the physics. Low-frequency bass notes have these really long, powerful waves. They don't just tap on the wall, they have enough energy to make the entire structure resonate, turning your wall into one giant fuzzy speaker. The shorter, higher frequency waves for the vocals just aren't as powerful, so they get absorbed or reflected way more easily.
So what's next? The future is pretty wild. Scientists are working on things called acoustic metamaterials, stuff that's engineered at a microscopic level to literally bend and block sound waves. Or get this, smart walls that can actively listen for noise and then change their own properties to cancel it out in real time.
And that kind of leaves us with this final amazing thought. We've gone from just stacking up bricks to the very real possibility of active, intelligent sound control. I mean, can you imagine living in a world where you could just create your own personal bubble of perfect silence just by pressing a button? The science is already taking us there.